Subscribe to the channel so you don't miss out on any of these videos. Imagine an explosion so powerful, it not only creates a dazzling spectacle visible across vast stretches of space, but it also bursts the very elements that make up the world around us, the planets, and even life itself. This event, one of the most violent phenomena in the universe, occurs when two neutron stars collide, giving birth to a kilonova. In an instant, the forces at play are unimaginable. These are the kinds of events that make us question everything we think we know about space, time, and matter. Today, we're diving deep into one of the most mysterious and awe-inspiring events in the cosmos, the kilonova and the cosmic catastrophe that causes it, the collision of neutron stars. The universe has always been full of wonders and mysteries. Some of them, like black holes or supernovae, are relatively well understood. But then there's the kilonova. It's an event so mind-bogglingly powerful, and yet so rare that it almost seems too strange to be true. The violent collision of two neutron stars can release more energy than our Sun will in its entire lifetime. But that's just the beginning. From this explosive event, some of the heaviest and most complex elements in the universe are formed. And if that weren't enough, the collision sends ripples across spacetime, detected by the faintest of signals, gravitational waves. Let's explore this cosmic disaster, one that merges the extreme density of neutron stars, the explosive energy of a supernova, and the mysterious forces that govern the fabric of spacetime. It's a tale of destruction, creation, and the birth of the elements that shape the universe as we know it. Neutron stars themselves are strange. They are the remnants of massive stars that have exploded in a supernova. What's left after the explosion is a dense core, packed so tightly that it's a cosmic paradox. These stars, each of them roughly the size of a city, have a mass greater than our Sun. A single cubic centimeter of a neutron star weighs as much as a mountain. You can imagine the force involved when two of these incredibly dense objects meet. Now, imagine these two neutron stars spiraling toward each other, drawn in by the force of their own gravity. They orbit each other in a dance of death, each one tugging at the other with increasing force, until, in a final, catastrophic moment, they collide. This collision, lasting only a few seconds, is so intense it releases an unfathomable amount of energy, much of it in the form of a burst of electromagnetic radiation. This is the kilonova. A kilonova is the result of the neutron star merger, and its brightness and power dwarf many other cosmic events, rivaling even the might of supernovae in some ways. But unlike a supernova, a kilonova doesn't just shine bright because of an exploding star. The unique properties of the collision, and the way matter behaves under such extreme conditions, mean that a different kind of nuclear fusion takes place. This process is what produces some of the heaviest elements in the universe, things like gold, platinum, and uranium. Here's where it gets even more mind-blowing. The elements we see on Earth, including the metals in our jewelry, the gold in our electronics, and the uranium used in nuclear reactors, all have their origins in these catastrophic events. It's theorized that neutron star collisions are responsible for producing roughly half of the elements heavier than iron in the universe. All that precious metal, all those atoms in your body, have their roots in these violent, stellar collisions that occurred eons ago. But the impact of a kilonova goes far beyond just the creation of new elements. It sends out a shockwave of gravitational waves, ripples in spacetime itself. Gravitational waves were predicted by Albert Einstein over a century ago, but only in recent years have we been able to detect them. These waves are produced by massive, accelerating objects in space, like the merging of two neutron stars. The moment these stars collide, they release a pulse that travels through space, stretching and squeezing spacetime as it moves. It's an event so powerful that it can be detected across light years of distance. The first direct detection of gravitational waves from a neutron star collision came in 2017, and it sent shockwaves through the scientific community. For the first time, we weren't just seeing the light emitted by a cosmic event, we were feeling the very fabric of spacetime vibrating. This breakthrough confirmed a long-held theory and opened up an entirely new way of observing the universe. Through gravitational waves, we can now detect events that were previously invisible to our telescopes. Things that happen in the deepest reaches of space, events that take place billions of light years away, but whose echoes are just now reaching us. As amazing as these discoveries are, there's still so much we don't know about kilonovae and neutron star mergers. For instance, we're still learning about the exact conditions under which these events happen. How do the two neutron stars spiral together? What exactly causes them to collide? And when the kilonova happens, why do some produce more gold and others produce more uranium? These are all open questions, ones that continue to intrigue scientists and astronomers alike. To better understand how neutron stars collide, let's talk about the physics involved. When two neutron stars come close enough, their mutual gravitational attraction accelerates them toward one another. As they spiral inward, they're moving faster and faster. The force of gravity becomes so immense that it warps the fabric of spacetime around them. Eventually, this leads to the collision. The stars crash into one another at incredible speeds, releasing enormous amounts of energy in the form of radiation, gravitational waves, and shock waves. This collision triggers a rapid process known as our process nucleosynthesis, which is the creation of heavy elements. Under normal circumstances, fusion in stars only produces elements up to iron. But during a kilonova, the extreme environment and the shock waves from the collision provide the energy necessary for the fusion of much heavier elements. These are the elements that make up most of the heavy matter in the universe. When you look at the gold in your jewelry or the uranium in a nuclear power plant, you're looking at elements that were most likely forged in the death throes of neutron stars colliding. Scientists have developed models to try and predict the types of elements produced during these events. Some models suggest that a neutron star collision could produce vast amounts of platinum and gold, while others predict that the resulting kilonova could be rich in elements like iodine and thorium. These models are still being refined, and much of what we know is still theoretical. However, with each new observation, we are beginning to piece together the puzzle of how neutron star collisions help shape the chemical makeup of the universe. What's truly incredible is how these cosmic events connect to the very foundations of life on Earth. The elements produced during a kilonova can travel across space, drifting through interstellar clouds, where they may eventually find their way to a planet like ours. Over time, this process can lead to the formation of stars, planets, and even life. The story of a neutron star collision is also the story of how the building blocks of life came to be, a narrative that spans billions of years and stretches across the entire universe. When we observe these events, we're not just witnessing a spectacular cosmic explosion, we're looking at the birth of the elements that make up everything we know. And it doesn't stop there. The discovery of kilonovae has also opened new doors in astrophysics and cosmology. These events are giving us insight into the properties of neutron stars, the nature of gravity, and even the behavior of matter under extreme conditions. Yet, despite the breakthroughs in understanding these collisions, there's still much that remains mysterious. For instance, we don't fully understand the exact mechanisms behind the formation of neutron stars themselves. What triggers their collapse into such dense objects? And once two neutron stars collide, what happens to the material that gets ejected? Does it remain as solid matter, or does it eventually disperse into space, forming new stars and planets? The ejected material from a kilonova is one of the most fascinating aspects of these neutron star collisions. After the catastrophic merger, vast amounts of matter are blasted out into space. This material can form a rich, dense cloud of heavy elements that travel across the cosmos. While much of this ejected material is vaporized in the collision, the heavier elements that remain can seed the interstellar medium with gold, platinum, and other essential components for planetary systems. In this sense, the neutron star collision becomes a cosmic forge, creating elements that eventually find their way into new star systems and possibly new planets. One of the great mysteries of kilonovae is how the matter ejected from the collision behaves in the aftermath. When two neutron stars collide, they don't just explode in a single burst. The interaction between them can cause a series of ripples and shocks, and these can cause the ejected matter to form unusual shapes and structures. Some scientists speculate that this material might spread out in the form of a long, narrow jet, while others believe that the remnants of the stars could form a dense, rapidly spinning disk. Either way, the interaction of this ejected material with the surrounding space could be crucial in understanding the formation of new celestial objects. To add complexity, many of these collisions happen in regions of space that are hard to observe directly. Neutron stars are often found in binary systems, and when two of these systems collide, they can form a black hole, a final step in the merger process that makes them even harder to study. The formation of a black hole is often seen as the endgame for neutron star mergers, but the exact nature of this transition is still not well understood. How does the matter behave as it crosses the event horizon, the boundary beyond which nothing can escape? Does some of the material get ejected in a final burst, or is all of it sucked into the black hole? As we continue to unravel the mysteries of kilinovae, we've only scratched the surface of what they can tell us about the nature of the universe. The collision of neutron stars offers a laboratory for studying extreme physics in ways that were previously impossible. The energy released in a kilonova is so powerful that it can offer new insights into the behavior of matter at extreme temperatures and pressures. Scientists can study how gravity behaves in such extreme environments, and use this information to refine our understanding of Einstein's theories of relativity and the nature of spacetime itself. One of the ways we study kilinovae is through the detection of gravitational waves, which have opened an entirely new window into the universe. The first direct detection of gravitational waves in 2015, courtesy of the LIGO, Laser Interferometer Gravitational Wave Observatory, experiment, confirmed the existence of these ripples in spacetime. But it wasn't until 2 years later, in 2017, that scientists were able to capture gravitational waves from a neutron star collision, known as GW170817. This groundbreaking event was a game-changer in astrophysics, not only confirming the existence of kilinovae but also providing an unprecedented opportunity to observe these events from multiple angles. The detection of GW170817 allowed scientists to see a kilonova in real time. This event, which occurred about 130 million light-years away in the galaxy NGC 4993, was the first time astronomers were able to observe both the electromagnetic radiation and gravitational waves produced by a neutron star merger. It provided a wealth of data, enabling scientists to measure the amount of mass ejected in the explosion, the energy released, and even the distribution of heavy elements produced. It also allowed them to confirm the theory that neutron star mergers are responsible for the creation of heavy elements like gold and platinum. This was the first definitive evidence that such mergers could account for the vast quantities of these elements observed throughout the universe. The aftermath of GW170817 also gave us a glimpse into the potential future of astronomy. The ability to observe kilinovae through multiple channels, gravitational waves, electromagnetic radiation, and even neutrinos, marks a new era in our understanding of the cosmos. These multi-messenger observations provide a more complete picture of the event, offering us insights that go far beyond what we could ever hope to see with traditional telescopes alone. For the first time, we can study the full spectrum of cosmic phenomena, from the light we can see with our eyes to the faint ripples in spacetime that we can feel with our instruments. In the years since GW170817, scientists have become more adept at detecting and studying neutron star collisions, and their research has been instrumental in refining our understanding of kilinovae. Researchers are now looking for other events like GW170817, using both ground-based observatories and space telescopes to track down more neutron star mergers. Each new detection brings with it more clues to the mysteries of the universe. However, as advanced as our technology has become, there's still much that remains mysterious. For one, the rate at which neutron star mergers occur is still unclear. It's difficult to estimate how often these events happen, especially when we can only observe a tiny fraction of the universe. Some studies suggest that neutron star mergers might occur once every few 100,000 years in a given galaxy, while others propose a more frequent occurrence. Determining the true rate of these events could give us critical insights into the evolution of galaxies and the nature of stellar populations. Another mystery revolves around the precise physics of the neutron star collision itself. While we know that two neutron stars merge under the influence of their gravitational pull, We still don't fully understand how the material inside these stars behaves under such extreme conditions. Neutron stars are made of dense matter, so dense that even the protons and neutrons inside them are packed together to the point where normal physics breaks down. During a merger, the pressure and temperature become so high that the particles in the neutron star undergo rapid changes, leading to new states of matter and the creation of exotic substances. How exactly this happens is a subject of active research, and scientists are using advanced simulations and models to try to recreate these conditions in the lab. The final piece of the puzzle is understanding the long-term effects of neutron star mergers. When two neutron stars collide, they don't just vanish into thin air. The resulting explosion sends matter out into space, and this matter could form the building blocks for future stars and planets. Over time, these remnants will interact with other material in the interstellar medium, eventually contributing to the formation of new stellar systems. Some scientists even speculate that neutron star mergers could be the source of the mysterious high-energy cosmic rays that we observe coming from deep space. The possibility that neutron star mergers could be the origin of cosmic rays is intriguing, as these high-energy particles are among the most mysterious and energetic phenomena in the universe. Cosmic rays are primarily composed of protons, and while their origin is still debated, it's believed that many of them are accelerated in extreme environments, such as the aftermath of neutron star collisions. When neutron stars merge, the explosion releases vast amounts of energy, and this energy can accelerate particles to nearly the speed of light, potentially producing the cosmic rays we observe. The interaction between the particles released in a kilonova and the surrounding interstellar medium also plays a crucial role in how these events impact their local environments. The energy from the explosion could trigger the formation of new stars by compressing gas and dust in nearby molecular clouds. This process is known as star formation, and it's thought that the shockwaves generated by a kilonova could ignite the birth of new stars and even entire star systems. In this sense, neutron star collisions are not just destructive forces. They may also act as cosmic catalysts, facilitating the creation of new celestial bodies and adding to the dynamic evolution of galaxies. Another fascinating aspect of kilonovae is their potential to provide answers to some of the universe's most fundamental questions, such as the nature of dark matter. Dark matter is one of the greatest mysteries in astrophysics. Although we know it exists due to its gravitational effects on visible matter, we have yet to detect it directly. Some theorists speculate that neutron star mergers could shed light on dark matter by providing new ways to probe the unseen substance. Since kilonovae involve extremely dense environments and high-energy interactions, they could act as laboratories for studying dark matter's properties. For example, some researchers have proposed that the collision of neutron stars could produce particles that might interact with dark matter, offering an indirect way to detect its presence. The discovery of kilonovae and the subsequent research into these phenomena has also raised important questions about the future of space exploration. As our understanding of neutron star collisions deepens, we are gaining the tools to probe regions of space that were previously beyond our reach. With the development of more advanced space observatories, like the James Webb Space Telescope and next-generation gravitational wave detectors, scientists will be able to look further back in time and space, providing a clearer picture of the processes that shaped the universe. By observing kilonovae from different angles, at different wavelengths of light, and with the help of gravitational waves, we may be able to unlock even more secrets about the cosmos. One of the questions that still remains unanswered is how long these mergers last. While the actual collision takes place relatively quickly, on timescales of just a few seconds to minutes, the aftermath of a kilonova can continue for weeks or even months, with the explosion gradually fading as the energy dissipates. The length of time a kilonova remains visible depends on a number of factors, including the amount of material ejected, the density of the surrounding space, and the exact properties of the merging neutron stars. For instance, if the merger results in the formation of a black hole, the energy release may continue for a longer period, as the accretion disk surrounding the black hole can emit radiation for weeks after the event. On the other hand, if the merger doesn't produce a black hole, the event may fade more quickly. The study of kilonovae is not just important for understanding the physics of extreme environments. it also has profound implications for our understanding of the origin of life itself. Some scientists have suggested that the heavy elements produced by neutron-star mergers could play a critical role in the formation of life as we know it. Elements like gold, platinum, and uranium, which are thought to be produced in kilonovae, are essential for a variety of chemical processes that occur in living organisms. In this way, neutron-star collisions could have seeded the universe with the building blocks necessary for life, leading to a deeper philosophical question: are we, in a sense, made of stardust? While kilonovae are incredibly violent events, they also offer a glimpse into the universe's delicate balance between destruction and creation. The massive release of energy and the creation of heavy elements during a neutron-star merger can lead to the formation of new celestial objects, but these same processes can also trigger the collapse of entire star systems. The cyclical nature of these events, where destruction leads to creation, can be seen as a metaphor for the ongoing evolution of the universe. Just as stars are born, live out their lives, and eventually die, so too do the elements and forces within the universe, constantly reshaping and reordering the cosmos. The future of kilonova research is incredibly exciting. As more neutron-star collisions are detected and studied, scientists will continue to refine their models of how these events unfold. The study of kilonovae has the potential to revolutionize our understanding of astrophysics, cosmology, and the fundamental forces of nature. It may help to answer some of the most profound questions about the origin of the elements, the nature of gravity, and even the fundamental structure of the universe itself. As we learn more about these mysterious cosmic events, we will come to appreciate not just the scale of the forces at play, but the deep interconnectedness of the universe, where even the most violent collisions can lead to the creation of something new and beautiful. Yet, even as we uncover more about the nature of kilonovae, the universe seems to keep throwing more questions at us. For instance, how do we truly measure the rate of neutron-star mergers? The detection of such rare and explosive events requires advanced instruments capable of sensing gravitational waves and electromagnetic signals across vast distances. With only a few detected so far, the true frequency of these collisions remains uncertain. More detections will be necessary to fully understand how often these mergers occur and to build a more complete picture of their role in the cosmic cycle of creation and destruction. Moreover, there is still much to learn about the specific characteristics of the neutron stars involved in these mergers. Not all neutron stars are identical, and variations in their mass, size, and composition could affect the way they behave during a collision. Scientists are also investigating how the magnetic fields of neutron stars influence the outcome of their mergers. These magnetic fields are thought to be incredibly strong, perhaps up to 1,000 times stronger than those found in ordinary stars, and they could play a significant role in the dynamics of the merger process. One of the most profound questions is how neutron star mergers may contribute to the evolution of galaxies. In a universe teeming with stars, planets, and galaxies, the death of a pair of neutron stars could, in its own way, shape the future of entire galaxies. The heavy elements created in these explosions could be carried across vast distances, enriching the interstellar medium and providing the raw materials for the next generation of stars and planets. This highlights the importance of neutron star mergers not only as violent events but also as processes that are essential for the ongoing evolution of the cosmos. As our technological capabilities continue to improve, it's clear that the study of kilonovae will only deepen our understanding of the universe. The mysteries surrounding neutron star collisions will undoubtedly keep astronomers, physicists, and cosmologists busy for years to come, pushing the boundaries of our knowledge and challenging our perceptions of the cosmos. Whether they are producing gold and platinum, creating new star systems, or emitting gravitational waves that shake the fabric of space-time, kilonovae are a reminder that the universe is constantly evolving, always expanding, and forever full of hidden wonders waiting to be discovered. The study of kilonovae, which occur when neutron stars collide, remains one of the most fascinating and complex areas of astrophysical research. These events not only help explain the origins of heavy elements in the universe but also play a crucial role in shaping the universe's cosmic landscape. As we continue to detect more of these collisions and refine our models, the understanding of their properties and impacts is becoming richer, more nuanced, and more intricate. Let's delve deeper into some of the aspects that continue to drive research into these cosmic phenomena. One of the key areas of investigation in kilinovae research is the behavior of the heavy elements that are synthesized during the collision. Neutron-star mergers are believed to be one of the primary sources of elements like gold, platinum, uranium, and other heavy metals in the universe. Before the existence of kilinovae, scientists thought supernovae, catastrophic explosions of massive stars, were the primary source of these heavy elements. However, the discovery of kilinovae has shown that neutron-star mergers also play a crucial role in their creation. When neutron stars collide, the extreme conditions, such as intense heat and high-density matter, cause rapid nucleosynthesis, where lighter atomic nuclei fuse to form heavier elements. This process occurs within a few seconds to minutes of the collision and can result in the emission of gamma rays, X-rays, and other electromagnetic radiation. Observations of these radiation signals allow scientists to study the conditions under which these elements are created. For example, scientists have been able to detect light from kilinovae in multiple wavelengths, from ultraviolet light all the way to infrared, providing a window into the properties of heavy elements produced during these mergers. An interesting aspect of kilinovae is their role in understanding the cosmic history of the universe, especially in terms of chemical evolution. For example, astronomers have found that galaxies with higher rates of neutron-star collisions tend to have higher abundances of heavy elements like those produced in kilinovae. This could mean that neutron-star mergers are not only sources of heavy elements, but also indicators of galactic evolution. By studying the distribution and abundance of these heavy elements throughout different galaxies, scientists can gain insights into how stars and galaxies have evolved over time, including how the universe went from simple, primordial matter to the complex mix of elements that make up stars, planets, and life itself. Moreover, gravitational waves emitted by neutron-star collisions are essential tools for understanding these cosmic events. Gravitational waves are ripples in the fabric of spacetime caused by extremely massive and rapidly changing sources of energy, such as the merging of neutron stars. When two neutron stars collide, they emit gravitational waves that travel across space and are detected by instruments like LIGO, Laser Interferometer Gravitational Wave Observatory. By measuring the timing, frequency, and amplitude of these waves, scientists can determine not only the properties of the neutron stars involved but also the distance and the structure of the merger. The recent detections of gravitational waves from neutron star mergers have provided a goldmine of data for astronomers, helping to refine theories about how these events unfold and their role in creating heavy elements. Gravitational waves also allow scientists to see the universe in ways that are otherwise impossible. Unlike light waves that travel through space, gravitational waves provide a direct probe of spacetime itself, allowing astronomers to see directly through cosmic dust, gas clouds, and other obstructions. This makes them incredibly valuable tools for observing distant and obscured cosmic events like neutron-star collisions. By studying gravitational waves, scientists can directly observe phenomena like kilinovae that occur in regions of space far too dense or obscured for electromagnetic observations. This ability to see through dust and gas helps astronomers understand more about the dynamics of these cosmic collisions and the properties of the neutron stars involved. In addition to gravitational waves, researchers are also investigating the electromagnetic emissions associated with neutron star collisions. Electromagnetic emissions can provide crucial information about the environment in which a neutron star merger occurs, including the temperature, density, and composition of the ejected material. By analyzing how the light from a kilonova changes over time, fading from bright blue to red as it cools, scientists can learn a lot about the nature of the ejected material, how much energy was released, and the properties of the neutron stars involved. For example, observations of the electromagnetic counterpart of a kilonova event could help determine whether the collision resulted in a black hole or if the neutron stars survived the collision, merging directly into a single, more massive neutron star. The energy released during a neutron star collision can vary depending on the properties of the neutron stars involved. Some neutron star mergers produce a lot of energy, up to about 10% of the total energy output of the Sun. This energy is spread over a very short time scale, in terms of seconds to minutes, which is what makes these events so difficult to observe and study. However, when observed, the energy released during these collisions can be immense. For instance, a single neutron-star collision can release more energy than the sum of all stars in a galaxy over its entire lifetime. This energy release is crucial for powering the bright emissions that can be observed across different wavelengths of light, from gamma rays to visible light and beyond. Furthermore, the process of neutron-star collisions may play a role in shaping the larger structure of galaxies themselves. The elements produced during these collisions are carried away from the site of the explosion and spread throughout the surrounding galaxy. This enrichment process can have far-reaching implications, contributing to star formation, the chemistry of newly forming stars, and even the formation of planets. As elements like gold and platinum are distributed throughout the galaxy, they enrich the interstellar medium, adding heavy metals to molecular clouds, where stars form. This enrichment process, driven by neutron-star collisions, could be crucial for the formation of rocky planets like Earth, with their essential building blocks of heavy elements. One of the most profound implications of neutron-star collisions, however, is their role in the broader context of cosmic evolution. By understanding how neutron-star collisions create heavy elements, how they emit gravitational waves, and the broader galactic environment in which these collisions occur, scientists can build a picture of how the universe has evolved from its earliest moments to the present. The connection between neutron-star mergers and galaxy evolution, the formation of heavy elements, and the cosmic history is one of the central mysteries driving current astrophysical research. It ties together a diverse range of disciplines, from astronomy to physics, chemistry, and even cosmology. To fully understand neutron-star collisions, researchers rely on computer simulations to model the extreme conditions in these mergers. Simulating neutron-star collisions requires sophisticated mathematical models to capture the various forces involved: gravity, strong nuclear forces, and the behavior of superheated plasma. These simulations are run using supercomputers and attempt to recreate the process of neutron-star mergers, including how material is ejected, how energy is released, and how it interacts with surrounding space. The data generated from these simulations can then be compared against observations of actual neutron-star collisions, such as gravitational wave detections and electromagnetic emissions, to refine the models and improve our understanding of these cosmic events. In addition to computer simulations, scientists are also studying theoretical models of neutron-star behavior to understand the complex interplay between gravity, matter, and energy. For example, researchers are investigating how neutron stars could have exotic properties, such as superfluid interiors or super-strong magnetic fields, that might influence their behavior during a collision. By studying the behavior of neutron stars under extreme conditions, scientists can develop theoretical models that help predict the outcomes of these collisions and the properties of the resulting neutron star remnants, or black holes. The search for these elusive cosmic events, neutron-star collisions, is far from over. As our observational techniques improve and as we gain access to new data, such as gravitational wave detectors like LIGO and Virgo, astronomers are better equipped to detect these rare, violent collisions and understand their properties. The goal is to piece together the puzzle of how neutron stars behave during these collisions, their broader impact on the universe, and their role in cosmic evolution. While neutron-star collisions are among the most violent events in the universe, they also represent crucial building blocks for understanding the universe itself. Looking ahead, the study of neutron-star collisions and kilonovae will continue to be a vibrant and dynamic area of research. New discoveries are expected as we refine our techniques and improve our understanding of the universe. It is likely that the next decade will bring exciting new insights into the nature of neutron stars, the properties of matter under extreme conditions, and the evolution of galaxies. With the advent of new instruments, like next-generation gravitational wave observatories, more sensitive telescopes, and deeper data analysis, scientists will be able to explore the universe's most extreme environments in unprecedented detail. This ongoing quest to understand neutron-star collisions and their role in cosmic evolution is at the cutting edge of astrophysical research, with profound implications for our understanding of the universe. As our technology continues to evolve, one area that stands to benefit immensely from future advancements is the detection of kilonovae in other galaxies. While the discovery of kilonovae has been groundbreaking, it's still primarily confined to a relatively small region of the universe, close enough to Earth for current observational instruments to detect them. However, as telescopes become more sensitive and wide-ranging, it's likely that we will begin detecting kilonovae events in galaxies far beyond the Milky Way. This will allow scientists to study these phenomena on a much larger scale, gaining insights into their frequency and distribution across different types of galaxies. Understanding whether certain types of galaxies are more prone to neutron star mergers could provide important clues about the processes that drive galactic evolution. In particular, studying kilonovae in distant galaxies could help answer questions about the relative rates of neutron star mergers in different galactic environments. For example, do more massive galaxies experience more neutron star collisions? Or do smaller galaxies with high rates of star formation tend to produce more kilonovae? Investigating the relationship between galactic structure and kilonovae could help us understand the broader context in which neutron star mergers occur. It may also provide insight into the rate at which heavy elements are produced and how this impacts the chemical evolution of galaxies. A key aspect of this future research will likely involve space-based observatories. While ground-based telescopes like LIGO are already instrumental in detecting gravitational waves from neutron star mergers, there's a significant advantage to observing the universe from space. For one, space telescopes can observe wavelengths of light, such as X-rays and ultraviolet, that are blocked by Earth's atmosphere. This will allow astronomers to detect kilonovae more easily, especially those located in distant galaxies or obscured by cosmic dust. Additionally, space-based gravitational wave detectors could provide even more detailed measurements of these powerful cosmic events, enabling scientists to study them in greater depth. In terms of technological advancements, the next generation of telescopes, such as the James Webb Space Telescope, JWST, is expected to make significant contributions to the study of kilonovae. JWST's infrared capabilities will allow it to observe kilonovae in unprecedented detail, capturing light emitted during these events as it travels through space for billions of years. This could allow scientists to not only understand the properties of neutron star mergers but also learn more about the formation and evolution of galaxies and stars. By observing these events over time, astronomers could potentially track the evolution of kilonovae from the moment they occur to the fading remnants millions of years later. The detection of kilonovae is not only important for astrophysics, but also for a deeper understanding of the nature of matter and energy. These events involve extreme states of matter, such as neutron-rich material and highly compressed nuclear matter, that are not easily replicated in laboratories on Earth. By studying the behavior of matter under these conditions, scientists can test theoretical models of nuclear physics, including how nuclear reactions behave at the extreme densities found in neutron stars. For example, one of the most intriguing aspects of neutron star mergers is the way in which they produce heavy elements like gold and platinum. Understanding the precise conditions required to produce these elements could help refine our understanding of nuclear processes in general, opening the door to new insights into the behavior of matter under extreme conditions. Moreover, neutron star mergers also offer a unique opportunity to study the behavior of spacetime itself. The collision of two neutron stars generates gravitational waves, ripples in spacetime that can be detected across vast distances. By studying these waves, scientists can learn more about the fabric of spacetime, including how it behaves under the influence of incredibly strong gravitational fields. This has implications not only for our understanding of neutron stars and black holes but also for the broader field of gravitational physics. For example, gravitational wave detections could provide insights into the fundamental nature of gravity, and whether it behaves as predicted by Einstein's general theory of relativity in extreme environments. If deviations from these predictions are found, it could lead to groundbreaking discoveries in physics. One of the most exciting aspects of studying kilonovae and neutron star mergers is the prospect of discovering entirely new phenomena. The universe is full of mysteries, and every time scientists observe a new event, it can lead to questions that were previously unimagined. Neutron star mergers, in particular, may hold the key to understanding a variety of fundamental questions in astrophysics, from the creation of heavy elements to the nature of spacetime itself. As we continue to refine our detection capabilities and expand our knowledge of the universe, there may be unexpected surprises waiting to be discovered. As we explore these cosmic events in greater detail, scientists are also beginning to investigate how neutron-star mergers could potentially impact life here on Earth. While the odds of a neutron-star collision occurring close enough to Earth to have any direct effects are incredibly small, these events can still have an indirect impact on our planet. For example, the radiation emitted by a kilonova event could be detected by Earth-based telescopes, providing us with an early warning system for distant, catastrophic events. This could help astronomers better understand the frequency of these events and determine how often we might expect to observe them in the future. Moreover, the study of kilonovae and neutron-star mergers may one day help us answer some of the most profound questions about the origin of life and the universe. For example, did the elements required for life, such as carbon, nitrogen, and oxygen, come from the explosions of dying stars, or did they originate from neutron-star collisions? The precise role of neutron-star mergers in the creation of life's building blocks is still an open question, but as we continue to study these phenomena, we may come closer to answering it. Looking toward the future, the study of kilonovae is likely to remain one of the most exciting and rapidly evolving fields of research in astrophysics. With new observatories, improved simulations, and a deeper understanding of nuclear processes, scientists are poised to make groundbreaking discoveries about the universe's most extreme phenomena. These discoveries will not only enhance our understanding of neutron-star collisions but also shed light on the larger mysteries of the universe, from the formation of galaxies to the nature of spacetime itself. As we continue to unlock the secrets of kilonovae, one thing is clear: the study of neutron-star collisions is a journey that will continue to captivate and challenge scientists for generations to come. Every new discovery brings us closer to understanding the fundamental processes that govern the universe, and each breakthrough reveals a new layer of complexity that enriches our understanding of the cosmos. The future of kilonovae research is bright, and it promises to reveal some of the deepest secrets of the universe in the years and decades to come. As we stand on the cusp of what promises to be a new era in astrophysical research, the study of kilonovae and neutron-star mergers is poised to answer some of the most profound questions about the origins of the universe and the fundamental laws of nature. With each new discovery, scientists are refining their understanding of these incredibly violent events and their far-reaching consequences, not only for the universe at large but for the very building blocks of life as we know it. One of the most exciting developments on the horizon is the continued improvement in the precision of gravitational wave detectors. As more and more kilonovae are detected, researchers will be able to map the properties of neutron-star mergers with greater accuracy. By analyzing the gravitational waves emitted during these events, scientists can determine key factors such as the masses and spins of the neutron stars involved, as well as the properties of the material that is ejected into space. These details could offer profound insights into the internal structure of neutron stars, which remains one of the most enigmatic aspects of astrophysics. The question of how neutron stars form and evolve over time is still not fully understood. Neutron stars are thought to be born from the remnants of massive stars that have gone supernova. But what happens after the supernova, when these stellar remnants collapse under their own gravity? The dense core that remains is made almost entirely of neutrons, and it is so dense that a single teaspoon of neutron star material would weigh as much as a mountain on Earth. The precise physics of how these stars maintain their structural integrity, or why some of them end up in binary systems where they can eventually merge, is still a mystery. By studying the way these stars behave before, during, and after a kilonova event, scientists hope to gain a deeper understanding of the forces at play inside these bizarre and extreme objects. Another area of ongoing research is the role of kilonovae in the evolution of galaxies. While we've learned that neutron-star mergers can produce a wide array of elements, including some of the heaviest elements like gold and platinum, we're still trying to understand how these elements are distributed in galaxies over time. In particular, the role of kilonovae in the chemical enrichment of galaxies is an important question. Some astronomers suggest that kilonovae may play a major role in the formation of metal-rich environments in galaxies. The heavy elements created in these explosions are thought to spread out into the surrounding gas, enriching the interstellar medium and contributing to the formation of future generations of stars. This process could explain why some galaxies, particularly older ones, are richer in metals than others. It's also important to consider how kilonovae might affect the formation of planets in the future. The heavy elements produced during these explosions are essential for the creation of rocky planets like Earth, and their dispersal into the surrounding environment may be a key ingredient in the recipe for life. As these elements spread out across space, they may eventually find their way into the formation of new star systems, where they could contribute to the building blocks of new worlds. The study of kilonovae, therefore, may offer a unique window into the processes that shape planetary systems and even life itself. In this way, these cosmic events are not just of interest to astronomers and physicists, but also to astrobiologists, who are trying to understand how the elements necessary for life are distributed across the universe. One of the most intriguing aspects of kilonovae is their role in answering questions about the nature of dark matter and dark energy. These mysterious forces make up most of the mass-energy content of the universe, but they remain elusive and poorly understood. Some scientists hypothesize that the extremely high-energy environments created during neutron-star mergers could provide clues about the properties of dark matter. For example, it's possible that the gravitational waves emitted by kilonovae could reveal new insights into the distribution and properties of dark matter. Similarly, the study of these cosmic explosions might help researchers test theories about the nature of dark energy and its role in the accelerated expansion of the universe. While these ideas are still speculative, the potential for kilonovae to provide answers to some of the biggest mysteries in cosmology is one of the reasons why they continue to be such a focal point for scientific research. The possibility of using kilonovae to test the limits of our understanding of physics is another exciting avenue of research. While the collision of two neutron stars is an incredibly violent and destructive event, it also provides a natural laboratory for studying the laws of physics under extreme conditions. For example, neutron star mergers provide an opportunity to study the behavior of matter at ultra-high densities, where the usual laws of physics may no longer apply. In these environments, it's possible that new forms of matter, such as strange quark matter or even forms of exotic matter not yet discovered, could emerge. If these forms of matter exist, they could challenge our current understanding of nuclear physics, particle physics, and the fundamental forces of nature. As we look ahead, the next few decades will likely bring an unprecedented amount of data from both ground-based and space-based observatories. The continued improvement of gravitational wave detectors, such as the planned upgrades to LIGO and Virgo, will provide a wealth of new information about neutron star mergers. Space-based telescopes, like the James Webb Space Telescope, will give us unprecedented views of the light emitted by these events, allowing scientists to study the afterglow of kilonovae in more detail than ever before. In addition, upcoming missions like the European Space Agency's LISA, Laser Interferometer Space Antenna, will offer the ability to detect gravitational waves from a wider range of sources, including those originating from more distant kilonovae. In the near future, advancements in computer simulations will also play a key role in enhancing our understanding of kilonovae. These simulations, which model the behavior of neutron stars and their interactions, are becoming increasingly sophisticated. By simulating neutron star mergers, scientists can test different hypotheses about how these events occur and make predictions that can be compared to real-world observations. These simulations will help refine our understanding of the physics involved in neutron star collisions, from the behavior of matter under extreme pressures to the nature of the gravitational waves they emit. The study of kilonovae may also have practical applications beyond the realm of basic science. For example, the research conducted on neutron star mergers and their role in the creation of heavy elements may have implications for industries such as nuclear energy. By understanding the processes that create elements like uranium, scientists may be able to develop more efficient methods of generating energy, or even make advances in nuclear waste management. Additionally, the study of kilonovae and neutron star mergers could also lead to technological innovations in the field of gravitational wave detection, which could have applications in other areas of science and engineering. Despite the immense progress made in the past few decades, the study of kilonovae is still in its early stages, and there's so much more to discover. As technology continues to improve and more observations are made, we can expect to learn even more about these cosmic explosions and their role in the universe. From the creation of heavy elements to the mysteries of dark matter and dark energy, the study of kilonovae promises to unlock some of the most profound secrets of the cosmos. Looking even further ahead, the continued exploration of neutron star mergers and kilonovae could one day lead to discoveries that fundamentally alter our understanding of the universe. It's possible that the key to solving some of the deepest mysteries in physics, cosmology, and even the origins of life could be found in the aftermath of these explosive events. As we continue to study the violent and enigmatic world of neutron star collisions, we can only imagine the incredible discoveries that lie ahead. As we continue to explore the impact of kilonovae on our understanding of the universe, it's important to consider the broader implications of these violent cosmic events. The aftermath of a neutron star collision doesn't just end with the formation of heavy elements or the release of gravitational waves. The entire process is a catalyst for a wide range of scientific advancements that could shape how we understand the cosmos for generations to come. One of the biggest mysteries surrounding kilonovae is the specific mechanism by which these events produce such a vast array of elements, including some of the heaviest elements in the periodic table. While it's widely accepted that supernovae contribute to the creation of many elements, particularly those up to iron on the periodic table, neutron star mergers seem to produce elements far beyond that. Elements like gold, platinum, and uranium, which are some of the heaviest naturally occurring substances, are theorized to be formed during these violent collisions. The sheer amount of energy released during a kilonova is what allows these heavy elements to be synthesized, but how the neutron-rich material ejected from these mergers is processed into these elements is still not fully understood. What we do know, however, is that the production of these heavy elements has profound implications for the universe. These elements are not just important for the formation of planets or the development of life, but also for the very makeup of stars. The heavy elements created in kilonovae are thought to be spread across the surrounding space, eventually mixing with the interstellar medium. Over time, they may become part of new stars, planets, and even moons, contributing to the formation of more complex structures. In essence, these violent collisions are like cosmic factories, creating the raw materials for the next generation of stars and planetary systems. It's worth noting that while we've come a long way in our understanding of kilonovae, there's still much to be learned about the specific processes that govern these explosions. Researchers are using a variety of observational techniques to study these events in greater detail. For instance, astronomers are using advanced spectrographs to measure the light emitted by kilonovae, allowing them to identify the elements present in the explosion's aftermath. This helps scientists determine the distribution of elements within the ejected material, and refine their models of how these elements are produced during a neutron star collision. Additionally, the development of more sensitive gravitational wave detectors, such as the Laser Interferometer Space Antenna, LISA, and the next generation upgrades to LIGO, will allow scientists to detect kilonovae from farther distances and with greater precision. These advancements will provide an even more complete picture of these fascinating events, helping to answer questions that have puzzled astronomers for centuries. Beyond the immediate implications for astrophysics and cosmology, the study of kilonovae may also have a more profound philosophical significance. As scientists continue to investigate the origins of these events and their role in the universe, we are forced to confront fundamental questions about the nature of life and the universe itself. The fact that the elements that make up our planet, and even our very bodies, were forged in the explosive aftermath of neutron star mergers challenges us to reconsider our place in the cosmos. In a very real sense, we are made of stardust, and understanding the processes that give rise to the very elements that make life possible brings us closer to understanding the origins of life itself. Moreover, the study of kilonovae allows us to ponder the future of the universe. While we often think of stars as the engines that drive the cosmos, neutron stars and their collisions are playing a crucial role in shaping the universe's chemical landscape. As kilonovae continue to occur, They may shape the next chapter in the evolution of galaxies. We may even find that the next wave of star formation is influenced by the remnants of these cosmic explosions, with their heavy elements becoming the building blocks for future stars and planets. This insight into the future of the universe is one of the more fascinating aspects of kilinovae, as it gives us a glimpse into the ongoing processes that govern the evolution of galaxies over cosmic time. The idea that neutron-star collisions could play a central role in the formation of new stars and planets is not just a speculative notion but a key area of ongoing research. The ejecta from these mergers, enriched with heavy elements, could contribute to the enrichment of the interstellar medium, a crucial factor in the formation of future generations of stars. Furthermore, the gas clouds in galaxies may be influenced by the materials ejected from kilinovae, leading to a complex interplay between stellar death and rebirth. This feedback loop, where the death of neutron stars leads to the creation of new stellar systems, highlights the dynamic nature of the universe and the interconnectedness of cosmic events. As we look to the future, the exploration of kilinovae will likely become an even more central aspect of our scientific endeavors. New technologies, such as more powerful space telescopes and next-generation gravitational wave observatories, will allow us to peer deeper into the universe and detect these incredible events with greater precision. With the continued development of these technologies, it's possible that we will discover even more about the behavior of neutron stars and their role in the broader context of the universe's evolution. In particular, the role of kilinovae in the creation of heavy elements has the potential to revolutionize our understanding of not just astrophysics, but also the broader field of chemistry. By studying the way these elements are synthesized in the wake of neutron-star collisions, scientists could unlock new methods for producing these elements in the lab. While this may sound like a far-off possibility, the fact that kilinovae have already provided us with such valuable insights into the processes that shape the universe suggests that we are only beginning to scratch the surface of what's possible. One of the most exciting aspects of this research is the potential for collaboration across different fields of science. Astrophysicists, chemists, materials scientists, and even biologists could all benefit from a deeper understanding of the processes that govern the formation of elements in kilinovae. The interdisciplinary nature of this research underscores the profound connections between the various branches of science, and highlights the importance of continued collaboration in the pursuit of knowledge. The study of kilinovae is one of the most exciting frontiers in modern astrophysics, offering insights not only into the life and death of stars but also into the origins of the elements that make up our universe. These cosmic explosions are a testament to the incredible power of nature, and the more we learn about them, the more we uncover about the fundamental forces that shape the cosmos. As we continue to explore the mysteries of neutron-star collisions and their aftermath, we are not just learning about the universe. We are learning about ourselves and our place in the vast, interconnected web of existence. As the technological and observational tools at our disposal continue to evolve, the study of kilinovae promises to yield even more incredible discoveries in the years to come. From unveiling the secrets of dark matter and dark energy to revealing the origins of life itself, the potential for new knowledge is virtually limitless. In the end, it is the study of these extreme, violent events that might just help us unlock some of the deepest mysteries of the universe and our place within it. As we continue our journey into the vast and complex world of kilinovae, it's essential to examine the broader implications these events have on the universe. While the study of neutron-star collisions and their aftermath offers us insight into the formation of heavy elements and the behavior of gravitational waves, it also provides a lens through which we can better understand the nature of the universe itself. This exploration not only sheds light on the death of stars but also on the birth of galaxies and the interconnected processes that govern the evolution of cosmic structures over time. One key question that arises when studying kilinovae is how these events fit into the broader life cycle of the universe. The elements produced in neutron-star mergers are not only critical for the formation of planets and stars, but they also play an essential role in shaping the future of galaxies. Over time, the heavy elements ejected by kilinovae enrich the interstellar medium, providing the building blocks for the formation of new stars. The recycling of material between stellar generations is a fundamental process that drives the evolution of galaxies, ensuring that the cosmic cycle of life and death continues without interruption. In the case of galaxies, the presence of these heavy elements affects their overall structure and evolution. Galaxies are complex systems that go through various stages of life, from their initial formation to their eventual transformation into massive clusters of stars. The feedback from supernovae and kilonovae, the explosive deaths of stars and the subsequent enrichment of the interstellar medium, plays a crucial role in regulating star formation. This feedback mechanism helps govern how many new stars are born, the types of stars that form, and how the chemical composition of the galaxy changes over time. Furthermore, the energy released by kilonovae has the potential to influence the larger-scale structure of the universe. The gravitational waves emitted by these cosmic collisions travel across vast distances, and the detection of these waves allows us to probe the very fabric of space-time. This ability to measure the waves produced by kilonovae offers a unique opportunity to study the structure of the universe on the largest scales possible. Gravitational wave astronomy, still in its infancy, holds the promise of opening entirely new fields of exploration in cosmology. One of the most promising areas of research in the wake of the discovery of kilonovae is the investigation into the nature of dark matter and dark energy. These two mysterious components of the universe make up the majority of its mass energy content, yet their true nature remains unknown. Gravitational waves from neutron star mergers, combined with the study of the heavy elements produced in these events, might offer clues that could help unravel the mysteries of dark matter and dark energy. In particular, the study of the distribution of elements and the way in which they affect the gravitational waves that pass through space could reveal new insights into how these enigmatic forces operate. The role of kilonovae in the cosmic landscape also extends to the field of cosmology, particularly in relation to the expansion of the universe. Understanding how neutron star mergers influence the rate of star formation and the distribution of heavy elements throughout the universe could provide valuable information about the overall evolution of the cosmos. By studying the interaction between these cosmic events and the larger-scale structure of the universe, we may gain a better understanding of the forces that drive the expansion of the universe and how it will evolve in the future. In addition to their implications for cosmology, the study of kilonovae has the potential to reshape our understanding of the very nature of time and space. The gravitational waves emitted by these events are ripples in the fabric of space-time itself, and by measuring these waves, scientists can directly probe the structure of the universe on a level that was previously unimaginable. As we develop more advanced technologies for detecting and analyzing gravitational waves, we can expect to uncover even more profound insights into the fundamental workings of the universe. One exciting aspect of gravitational wave detection is that it offers us a direct way to study the properties of neutron stars and the behavior of matter under extreme conditions. These extreme environments, where matter is compressed to unimaginable densities and subjected to intense gravitational fields, provide an opportunity to test our theories of physics in ways that are not possible under normal conditions. By observing the gravitational waves produced by kilonovae, scientists can study the internal structure of neutron stars, gaining insights into their composition, the behavior of exotic matter, and the physics of dense, high-energy systems. Moreover, the study of kilonovae and gravitational waves has the potential to bridge the gap between different fields of physics. While much of modern physics is based on theories developed in laboratories here on Earth, the extreme conditions found in space provide a unique environment to test these theories in ways that are not possible on our home planet. The violent collisions of neutron stars are essentially natural laboratories that allow scientists to probe the behavior of matter and energy under the most extreme conditions. This cross-disciplinary approach could lead to breakthroughs in both theoretical and experimental physics, advancing our understanding of the fundamental laws that govern the universe. Looking forward, the study of kilonovae will continue to expand our knowledge of the universe in ways we can't yet fully predict. As our detection methods improve, we will be able to observe these cosmic events with ever greater precision. This will allow us to learn more about the specifics of neutron star collisions, the exact processes that lead to the formation of heavy elements, and the role that kilonovae play in the evolution of galaxies. The future of kilonovae research is not just about answering questions. It's about uncovering entirely new lines of inquiry that we have not yet even thought to explore. The more we learn about the behavior of neutron stars, the creation of heavy elements, and the dynamics of gravitational waves, the more we realize how much we have yet to discover about the universe. These cosmic events are windows into the deepest mysteries of the cosmos, and the study of kilonovae is poised to shape the next era of scientific exploration. Kilonovae represent a frontier of knowledge in modern astrophysics. These violent collisions of neutron stars do not just provide a spectacular show of cosmic fireworks. They reveal the underlying processes that drive the evolution of the universe itself. From the production of heavy elements to the emission of gravitational waves, the study of kilonovae opens up new avenues for research in a variety of scientific fields, from astrophysics and cosmology to chemistry and materials science. As our technology advances and our understanding deepens, the exploration of kilonovae promises to continue to be one of the most exciting and rewarding areas of scientific inquiry, offering a glimpse into the very fabric of the universe and the forces that shape its destiny. As we venture deeper into the study of kilonovae and their role in the cosmos, it's important to explore how these rare events have affected our understanding of the universe's past and future. The collision of neutron stars, once thought to be an obscure and isolated phenomenon, has proven to be a powerful tool for unraveling some of the most fundamental questions about the universe's evolution. From the creation of heavy elements to the study of gravitational waves, these cosmic collisions continue to challenge our perceptions and open new realms of discovery. The connection between kilonovae and the origins of heavy elements is one of the most fascinating aspects of these events. Before the discovery of kilonovae, scientists knew that supernovae were the primary source of many of the universe's heavy elements, such as gold, platinum, and uranium. However, it was unclear how these elements were formed in such large quantities and with the precision that we observe in the universe today. When the first kilonova was observed in 2017, following the detection of a gravitational wave event from two colliding neutron stars, the scientific community was shocked to learn that neutron star mergers were responsible for producing a significant portion of the universe's heaviest elements. This discovery was not only revolutionary in its own right but also had profound implications for our understanding of stellar evolution and nucleosynthesis. Before this discovery, the leading theory of element formation suggested that supernovae were the primary engines behind the creation of heavy elements. While supernovae certainly play a role in the production of some elements, kilonovae appear to be responsible for a much larger portion of these materials, particularly those elements that are much heavier than iron. The energy released in the violent collision of neutron stars is capable of synthesizing these rare elements in quantities that are not only significant but also necessary for the formation of planets, stars, and the very building blocks of life itself. But how does this process work? And why are neutron star collisions so effective at producing such heavy elements? To understand this, we must first examine the extreme conditions that are created during a kilonova. When two neutron stars collide, the energy generated is incomprehensibly immense. The collision results in the rapid fusion of matter at incredibly high temperatures and densities. In this environment, the forces at play are strong enough to overcome the usual nuclear barriers, allowing atoms to fuse together and form elements that would otherwise be impossible to create. This process, known as our process nucleosynthesis, is responsible for the creation of many of the heaviest elements in the periodic table. It occurs when atomic nuclei rapidly capture neutrons, fusing them together to form progressively heavier elements. This process requires an environment where there is a large abundance of free neutrons and extreme conditions that allow for rapid neutron capture. Neutron star mergers provide exactly the right conditions for this process to take place, leading to the production of elements such as gold, platinum, and uranium, elements that are vital for the formation of planets and life as we know it. The R process is not limited to just one type of astronomical event, but the extreme conditions present during a kilonova make it one of the most efficient sites for the production of these heavy elements. The discovery of kilonovae has thus changed the way we think about the origins of some of the universe's most precious materials. Gold and platinum, for example, which were once thought to be formed primarily in the interiors of stars, are now known to have been produced during these catastrophic neutron-star collisions. In fact, the amount of heavy elements produced in these collisions is likely to be on par with or even greater than the amount produced in all the supernovae combined over the course of the universe's history. As we continue to learn more about kilonovae and their role in the formation of the elements, we are also gaining valuable insights into the behavior of matter under extreme conditions. The neutron stars involved in these collisions are some of the densest objects in the universe, with a mass greater than that of the Sun packed into a volume no larger than a city. The intense gravitational fields around these stars warp spacetime in a way that allows scientists to test our understanding of the laws of physics in a regime that cannot be replicated on Earth. By studying the aftermath of these collisions, we can gain insight into the properties of neutron stars, the nature of nuclear matter, and the behavior of gravity in the most extreme environments imaginable. This brings us to another crucial aspect of kilonovae, the gravitational waves they emit. Gravitational waves are ripples in the fabric of spacetime, created by the acceleration of massive objects, such as the collision of neutron stars. These waves travel at the speed of light, and carry with them information about the event that generated them. By detecting and analyzing these waves, scientists are able to learn about the physical properties of the objects involved in the collision, as well as the processes that took place during the event. The detection of gravitational waves has opened up a whole new realm of astronomy, allowing us to study phenomena that were previously invisible to traditional telescopes. Gravitational wave observatories, such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo, have already made groundbreaking discoveries, including the detection of the first-ever gravitational wave signal from a binary black hole merger in 2015. However, it was the detection of the kilonova, GW170817, in 2017 that truly marked the beginning of gravitational wave astronomy. For the first time, scientists were able to directly observe both the gravitational waves and the electromagnetic radiation emitted by a single astrophysical event. This discovery not only confirmed the existence of kilonovae but also provided crucial data about the nature of neutron star mergers, their role in the production of heavy elements, and the behavior of gravitational waves. The significance of this discovery cannot be overstated. Prior to the detection of gravitational waves from neutron star mergers, the only way to study such events was through electromagnetic radiation, such as light, radio waves, and X-rays. However, gravitational waves offer a unique way to study the dynamics of these events without relying on the limitations of traditional telescopes. Gravitational waves are able to travel through the universe without being scattered or absorbed by matter, which means that they can provide a clearer, more direct picture of what is happening during these violent events. They also allow us to study objects that are otherwise invisible, such as black holes and neutron stars, which do not emit light in the traditional sense. As we continue to detect more gravitational wave signals from kilonovae and other cosmic events, our understanding of the universe will continue to evolve. These waves offer us a way to probe the deepest mysteries of the cosmos, from the behavior of exotic matter to the structure of spacetime itself. In the coming years, we can expect even more groundbreaking discoveries as the sensitivity of gravitational wave detectors improves and our ability to analyze the data becomes more sophisticated. Ultimately, the study of kilonovae is just one piece of the larger puzzle of understanding the universe. By exploring the ways in which neutron star collisions produce heavy elements, generate gravitational waves, and shape the evolution of galaxies, we are gaining a deeper appreciation for the intricate connections between the smallest and largest scales of the cosmos. Each new discovery brings us closer to answering some of the most fundamental questions about the nature of the universe and our place within it. From the formation of the heaviest elements to the detection of gravitational waves, the study of kilonovae is helping to reveal the complex, dynamic, and ever-evolving nature of the cosmos. As we look ahead, it's clear that kilonovae will continue to be a key area of research in astrophysics and cosmology. The insights we gain from studying these cosmic collisions have the potential to revolutionize our understanding of the universe and shape the future of scientific inquiry for generations to come. Whether through the discovery of new heavy elements, the detection of more gravitational waves, or the continued study of neutron stars and their behavior, the mysteries of kilonovae will remain one of the most exciting and rewarding areas of exploration in the cosmos. As we move forward with this exploration of kilonovae and the vital role they play in understanding the universe, it's important to consider the broader implications of these events. The process of neutron star mergers is just one of many high-energy phenomena that challenge the boundaries of our understanding of physics. However, the study of kilonovae allows us to not only probe the nature of matter under extreme conditions but also sheds light on fundamental cosmic processes that influence the formation of galaxies, stars, and planetary systems. In essence, the study of neutron star collisions is a window into the very heart of the cosmos, offering an unprecedented look at the forces that govern the universe's most dramatic events. One of the most fascinating aspects of kilonovae is their role in shaping the evolution of galaxies and the chemical enrichment of the cosmos. For billions of years, stars have been at the center of the universe's ongoing process of nucleosynthesis, the creation of elements through the fusion of atomic nuclei. While stars like our Sun primarily produce lighter elements like hydrogen, helium, and carbon, it's the more massive stars that forge the heavier elements, such as iron, nickel, and oxygen, through the process of stellar nucleosynthesis. But what happens when a star dies? How does the universe get the even heavier elements, like gold and uranium, that we see today? This is where kilonovae come into play. The explosion of a neutron star collision provides an intense enough environment to facilitate the creation of the heaviest elements, including those that make up the core of planets, the substance of life, and the precious materials we find on Earth. It turns out that these catastrophic events are not just violent cosmic spectacles, they are the essential cosmic factories that provide the raw material necessary for the formation of new stars, planets, and even life itself. Kilonovae are a crucial part of the universe's recycling process, enriching the interstellar medium with the heavy elements that will go on to form new generations of stars and planets. Moreover, the collision of neutron stars and the resulting kilonova explosion also influences the structure of galaxies. These events are thought to be a significant contributor to the process of galaxy formation and evolution. As heavy elements are dispersed into the surrounding space, they contribute to the overall chemical makeup of the galaxy. Over time, this material clumps together, forming new stars and planetary systems. Without the contribution of neutron star mergers, the process of galactic evolution would be much slower, and the complexity of planetary systems, like our own, would be drastically reduced. Kilonovae also provide valuable insights into the behavior of matter in extremely dense environments. Neutron stars, the remnants of massive stars that have exploded in supernovae, are among the densest objects in the universe. A neutron star is so dense that a single cubic centimeter of its matter would weigh as much as the entire mass of Mount Everest. This density is the result of the collapse of a massive star's core after it exhausts its nuclear fuel. The collapse is so extreme that protons and electrons combine to form neutrons, creating a star made almost entirely of neutrons. These neutron stars are incredibly small, about the size of a city, yet they possess a mass several times greater than that of the Sun. Understanding how neutron stars behave, particularly during mergers, is essential for expanding our knowledge of nuclear physics and the behavior of matter under extreme conditions. When two neutron stars collide, they form a remnant object that may become a black hole or a highly magnetized neutron star, depending on the mass of the two original neutron stars. The immense gravitational forces involved in such a merger cause the matter to be compressed to incredible densities, providing scientists with a natural laboratory to study the properties of matter under conditions that cannot be replicated on Earth. These conditions are so extreme that they challenge our understanding of the laws of physics, particularly with respect to the behavior of gravity. The gravitational forces during a neutron star collision are strong enough to warp spacetime itself, producing gravitational waves that can be detected on Earth. These ripples in spacetime provide scientists with a unique way to study the universe's most energetic phenomena without the limitations of traditional telescopes. By detecting these gravitational waves, scientists are able to directly measure the properties of neutron stars, black holes, and other exotic objects, which were previously invisible to us. The detection of these gravitational waves, such as those from the GW170817 event in 2017, has opened up an entirely new field of astronomy known as gravitational wave astronomy. Prior to this discovery, our understanding of the universe was based almost entirely on electromagnetic radiation, light, radio waves, and X-rays. Gravitational waves offer an entirely new way to observe the universe, allowing scientists to study phenomena that are invisible to traditional telescopes. This is especially important for understanding the behavior of neutron stars and black holes, as these objects do not emit light in the traditional sense. Gravitational waves allow us to study their properties directly, providing invaluable insights into their formation, evolution, and role in the cosmos. Looking forward, the study of kilonovae will likely continue to be one of the most exciting areas of astrophysical research. As technology improves, particularly in the detection of gravitational waves and the observation of electromagnetic radiation from neutron star mergers, scientists will be able to gather even more data about these events. This will help to refine our understanding of the fundamental processes that govern the universe, such as the creation of heavy elements, the behavior of matter under extreme conditions, and the dynamics of neutron-star collisions. Additionally, the study of kilonovae is likely to provide key insights into the expansion of the universe and the mysteries of dark energy. While the exact nature of dark energy remains one of the biggest unanswered questions in cosmology, it's possible that neutron star mergers may hold clues about the role that dark energy plays in the accelerating expansion of the universe. The more we learn about the behavior of massive objects like neutron stars and black holes, the more we can infer about the underlying forces shaping the universe. In a broader sense, the study of kilonovae is not just about understanding specific cosmic events. It's about unlocking the secrets of the universe itself. These events allow us to probe the deepest questions of physics and astronomy, from the nature of matter to the structure of space-time. They challenge our understanding of the universe and push the boundaries of scientific knowledge, revealing new layers of complexity in the fabric of the cosmos. As we continue to make breakthroughs in gravitational wave detection, observe more kilonovae, and improve our ability to simulate these extreme events in the laboratory, the mysteries surrounding neutron star mergers will only deepen. Each discovery brings us one step closer to understanding the true nature of the universe, and each kilonova provides us with another piece of the cosmic puzzle. Ultimately, the collision of neutron stars represents a unique and awe-inspiring process that encapsulates the fundamental forces of the universe. These violent cosmic events, which produce heavy elements, emit gravitational waves, and challenge our understanding of physics, remind us of the immense power and beauty that exist beyond our planet. By studying kilonovae, we not only gain insights into the life cycles of stars and the formation of galaxies but also edge closer to answering some of the most profound questions about the nature of existence itself. Kilonovae serve as one of the universe's most incredible showcases of the forces at play in the cosmos. Their magnitude, not just in terms of energy released, but in their ability to contribute to our understanding of the universe, is staggering. They offer insights into the deepest elements of astrophysics and cosmology, providing a glimpse into the fundamental processes that govern the very fabric of space-time. As we continue to probe deeper into the aftermath of these neutron star collisions, it becomes clear that we are uncovering clues about the universe that we could never have anticipated. For example, one of the key findings from the study of kilonovae is how they challenge the traditional understanding of the universe's rate of expansion. In 1998, the discovery that the expansion of the universe was accelerating led to the hypothesis of dark energy, a mysterious force that counteracts the gravitational pull of matter and causes the universe to expand faster over time. However, dark energy remains largely unknown, and scientists have struggled to understand its true nature. Some theorists speculate that the study of neutron star mergers and kilonovae could provide key evidence for how dark energy works and how it might influence the large-scale structure of the cosmos. While the direct connection between kilonovae and dark energy is still unclear, it's an area of active research that could reveal unexpected breakthroughs. The direct observation of kilonovae also challenges our assumptions about the relationship between gravity and the creation of the heaviest elements in the universe. For a long time, scientists had thought that the majority of these elements were formed through the supernova explosions of massive stars. However, the discovery of kilonovae has introduced a new player in this cosmic drama. The extreme conditions during a neutron-star collision, combined with the incredible density and speed of the stars involved, create a dynamic environment that is capable of synthesizing some of the heaviest and most elusive elements. This includes elements like gold, platinum, and uranium, which, as mentioned earlier, are crucial to the chemical makeup of planets and the formation of new stars. The fact that these elements could be formed in the wake of a neutron-star collision expands our understanding of nucleosynthesis and the ways in which the universe is constantly recycling material to form new structures. Moreover, the discovery of kilonovae has profound implications for our understanding of black holes. When two neutron stars merge, they often create a massive, highly energetic explosion. This explosion can sometimes result in the formation of a black hole. However, the exact conditions that determine whether a black hole will form, versus a neutron star remnant, are still not fully understood. By observing multiple kilonovae and the resulting remnants, astrophysicists are gradually piecing together the puzzle of black hole formation. This will help refine our understanding of these enigmatic objects, which remain some of the most fascinating and mysterious features of the universe. Another aspect of kilonovae that holds immense significance is the opportunity they provide for testing the laws of physics in extreme environments. As neutron stars collide, they undergo intense gravitational interactions that can cause distortions in spacetime itself. These interactions produce gravitational waves, ripples in the fabric of spacetime that travel outward from the point of collision. These waves carry information about the properties of the colliding objects, offering a direct means to study the behavior of matter under extreme conditions. The study of gravitational waves is still a relatively young field, but the detection of these waves from kilonovae events has already revolutionized our understanding of astrophysics and cosmology. Gravitational wave astronomy, sparked by the groundbreaking detection of waves from the 2015 LIGO Laser Interferometer Gravitational Wave Observatory experiment, has already provided many significant revelations. However, the observations of kilonovae through gravitational waves have expanded our understanding of the cosmos even further. Prior to these discoveries, astrophysics had been primarily reliant on electromagnetic radiation, such as visible light, X-rays, and gamma rays, to study cosmic events. Gravitational waves, on the other hand, offer a unique perspective, revealing information about celestial phenomena that would otherwise be invisible to traditional telescopes. For instance, the 2017 event GW170817, the first ever detection of gravitational waves from a neutron-star merger, not only confirmed the existence of kilonovae but also provided a wealth of new data. This event marked a landmark moment in our understanding of how the universe works. Not only did it provide direct evidence of the synthesis of heavy elements like gold and platinum, but it also confirmed the creation of a short gamma-ray burst, which had long been theorized to be the result of such collisions. Moreover, this discovery opened up an entirely new chapter in astronomy, one where gravitational waves and electromagnetic observations are combined, creating a more comprehensive picture of the most dramatic and energetic events in the universe. The study of kilonovae through gravitational wave observations allows scientists to make direct measurements of things that were once purely theoretical. For example, the collision of two neutron stars offers an opportunity to study the behavior of matter at densities far beyond what is achievable in laboratories on Earth. These extreme environments give scientists a glimpse into the mysteries of nuclear physics, including how matter behaves at these high densities and the role of strong nuclear forces in these interactions. Beyond their role in the creation of heavy elements and the study of gravity, neutron-star collisions also offer a new way to investigate the end stages of massive stars. While much of the focus in stellar evolution has been on the collapse of stars into black holes after a supernova, neutron stars themselves represent another possible fate for stars with masses that are too small to collapse directly into black holes. By studying how neutron stars behave as they merge, we can learn more about the life cycles of stars that exist in the mass range between supernova progenitors and black holes. These insights are vital for painting a more complete picture of the processes that occur in the final stages of a star's life, and how these processes influence the broader structure of galaxies. The potential for future discoveries in this field is immense. As gravitational wave detectors continue to improve in sensitivity, and as our understanding of astrophysical phenomena deepens, the study of kilonovae will only grow more important. The fact that neutron-star mergers can be detected through both gravitational waves and electromagnetic radiation opens up a wealth of observational possibilities. With more advanced telescopes and gravitational wave observatories, scientists will be able to observe even more kilonovae, allowing for a more detailed understanding of their mechanics, their role in the universe, and their connection to other cosmic phenomena. The more we learn about kilonovae, the more we realize just how crucial these events are in shaping the universe. From the formation of heavy elements to the creation of black holes, from the emission of gravitational waves to the study of matter under extreme conditions, neutron-star collisions touch on nearly every aspect of modern astrophysics. These violent, cataclysmic events are not just extraordinary displays of the universe's power, they are essential to understanding the nature of the cosmos itself. As we continue to explore this exciting field of study, one thing is certain: the mysteries of kilonovae will continue to fascinate and inspire us for years to come. As the study of kilonovae progresses, researchers are not only delving into the aftermath of these cosmic cataclysms, but also uncovering new layers of the physics that govern the most extreme environments of the universe. One of the most intriguing aspects of kilonovae is their role in unraveling the mysteries surrounding the equation of state, EOS, of neutron stars. The equation of state is essentially a mathematical model that describes how matter behaves under the extreme conditions of density and pressure found inside a neutron star. The EOS of neutron stars is a central question in astrophysics, as it determines the relationship between the mass and radius of a neutron star and dictates whether a neutron star can survive after a collision or collapse into a black hole. By studying the gravitational waves emitted by neutron-star mergers and analyzing the properties of the kilonova explosions they produce, scientists are able to place more constraints on the EOS of neutron stars. The merger event GW170817, for example, provided valuable insights into the composition of neutron stars and the nature of the high-density matter inside them. Observations of the event, including the detection of gravitational waves and the corresponding electromagnetic signals from the kilonova, revealed key details about the neutron star's size, mass, and the strength of the nuclear forces at play. Such findings help researchers refine models of neutron star interiors, giving us a more accurate picture of the fundamental forces at work in these objects. Furthermore, the study of neutron-star mergers also has implications for understanding the broader question of how matter behaves at extreme densities. Neutron stars, which are the remnants of massive stars that have exhausted their nuclear fuel, are incredibly dense, with a mass greater than that of the Sun packed into a space the size of a city. The study of neutron stars, and in particular their mergers, allows scientists to probe matter at densities far beyond what we can achieve in laboratories on Earth. This opens up exciting possibilities for testing the limits of our current understanding of nuclear physics, as well as for exploring the strange and often counterintuitive properties of matter under such extreme conditions. The role of kilonovae in producing heavy elements like gold, platinum, and uranium also cannot be overstated. These elements are created through a process known as rapid neutron capture, or the R process. The R process occurs when atomic nuclei rapidly capture neutrons, leading to the creation of heavier elements. While the R process has long been associated with supernovae, it is now understood that neutron-star mergers play a significant role in this process. The intense heat and pressure generated by the collision of two neutron stars provide the perfect environment for the R process to occur, resulting in the formation of these heavy elements. In fact, it's believed that a significant portion of the universe's supply of gold and other heavy elements may have been forged in the wake of neutron-star mergers. The discovery of kilonovae has sparked a reevaluation of the origins of these precious metals. Before the observation of neutron-star mergers, it was widely assumed that the vast majority of heavy elements in the universe were created in the explosive environments of supernovae. However, the evidence from kilinovae suggests that these mergers are just as important, if not more so, in the creation of elements like gold and platinum. This has profound implications for our understanding of stellar evolution and the chemical evolution of galaxies. If neutron-star mergers are indeed responsible for a significant portion of the heavy elements in the universe, it means that these collisions are not only shaping the structure of the cosmos but also contributing to the very building blocks of life itself. The discovery of kilinovae also has broader implications for the field of cosmology. One of the most important aspects of cosmology is understanding the origins of the universe and the processes that led to its current state. The study of kilinovae, and the insights they provide into the formation of heavy elements and the evolution of neutron stars, offers a unique window into the early stages of the universe. The heavy elements produced in neutron star mergers are thought to have contributed to the formation of planets and stars, and understanding the role of these mergers in the creation of these elements could help us better understand the chemical makeup of the universe. In addition to their role in producing heavy elements, kilinovae also provide valuable information about the expansion of the universe. The detection of gravitational waves from neutron star mergers has allowed scientists to make more accurate measurements of the Hubble constant, which describes the rate at which the universe is expanding. The Hubble constant is a fundamental parameter in cosmology, and its precise value has been a subject of intense debate among scientists. The observation of kilinovae provides a new way to measure the expansion rate of the universe, potentially resolving some of the discrepancies between different methods of measuring the Hubble constant. This has far-reaching implications for our understanding of the universe's age, its size, and its ultimate fate. In the coming years, as gravitational wave observatories continue to improve in sensitivity, and as new telescopes are deployed to observe kilinovae in greater detail, we are likely to witness even more groundbreaking discoveries in the field of neutron-star mergers. The study of these events will continue to push the boundaries of our knowledge, helping us answer some of the most fundamental questions about the nature of the universe and the forces that govern it. From the creation of heavy elements to the study of black hole formation, from the detection of gravitational waves to the exploration of matter at extreme densities, the study of kilinovae is one of the most exciting frontiers in modern astrophysics. Moreover, the possibility of future kilinovae events being observed by new, advanced observatories promises to open up an even deeper understanding of the cosmos. As scientists develop more powerful telescopes and more sensitive gravitational wave detectors, we may be able to observe the aftermath of even more neutron-star mergers. This will not only allow for a more detailed study of the mechanics of kilinovae but also provide a better understanding of the impact these events have on the surrounding universe. Each new observation will add another piece to the puzzle, bringing us closer to unraveling the mysteries of the universe's most violent and energetic events. The study of kilinovae is one of the most fascinating areas of modern astrophysics, offering insights into the most extreme environments of the universe. From their role in producing heavy elements to their contribution to our understanding of gravity and black holes, neutron-star mergers and the resulting kilinovae provide a wealth of information about the cosmos. As we continue to study these events, we are likely to uncover even more surprises and revelations about the nature of the universe and the forces that shape it. The mysteries of kilinovae are far from solved, and each new discovery brings us one step closer to understanding the fundamental processes that govern the cosmos. The mysteries surrounding kilinovae do not just lie in their observable phenomena but also in their deeper implications for cosmic history and the origins of matter. When considering the role of neutron-star collisions in producing heavy elements, it's crucial to examine their contributions to the periodic table as a whole. Before the first confirmed detection of a kilonova, astrophysicists had long theorized that supernovae were the primary factories of elements heavier than iron. Yet, the rarity and specific conditions required for the R process to occur raised questions about whether supernovae alone could account for the observed abundance of elements like gold and platinum in the universe. Neutron-star mergers provide the missing piece in this cosmic puzzle. The gravitational waves from these events give us insight into the violent nature of these collisions, but the light from the accompanying kilonova unveils the true treasure, the creation of elements through nucleosynthesis. As neutron stars spiral toward each other, they eject vast amounts of neutron-rich material into space. Within milliseconds, the intense heat and pressure trigger a cascade of reactions, leading to the rapid formation of heavy nuclei. This explains why kilonovae are so rich in these precious elements, reshaping our understanding of how and where such materials are formed. The discovery of kilonovae has even transformed how we think about our own planet. Earth's crust contains significant amounts of gold, platinum, and other heavy elements that could not have been formed in the early stages of the universe. These elements were instead forged in cataclysmic events like kilonovae and later distributed throughout galaxies, eventually becoming part of the molecular clouds from which our solar system was born. This means that every piece of jewelry, every electronic device containing rare metals, and even the elements in our bodies are, in some sense, remnants of ancient neutron star collisions. This realization adds an emotional dimension to the study of kilonovae. It connects humanity to the cosmos in a profound way, showing that the building blocks of life and civilization were created in some of the most extreme events imaginable. These elements, formed billions of years ago in distant parts of the universe, traveled through space and time, eventually coalescing into the planets and stars we see today. Without these mergers, the universe as we know it would lack many of the materials essential to life and technology. As we expand our observational capabilities, kilonovae also serve as natural laboratories for testing fundamental physics. For instance, they allow us to study the behavior of matter under conditions that cannot be replicated on Earth. Neutron star mergers involve matter at densities millions of times greater than anything we can achieve in a laboratory. Understanding how such matter behaves, particularly during the violent compression and ejection phases of a merger, provides insights into nuclear physics, quantum mechanics, and the behavior of exotic particles. Moreover, kilonovae offer unique opportunities to test Einstein's theory of general relativity in extreme environments. The detection of gravitational waves from neutron star mergers has already confirmed some of Einstein's predictions about the warping of spacetime. However, these events may also reveal deviations from the theory, potentially pointing to new physics. For example, if gravitational waves behave differently under the immense pressures of a kilonova, it could provide evidence for theories that extend beyond general relativity, such as string theory or quantum gravity. In addition to their scientific significance, kilonovae have become cultural icons, sparking public fascination and inspiring art, literature, and even philosophical reflections on humanity's place in the universe. The sheer scale and power of these events, combined with their role in shaping the cosmos, make them a source of wonder and a reminder of the universe's vastness and complexity. They challenge us to think about our origins and our interconnectedness with the cosmos, offering a humbling perspective on our existence. One of the most exciting prospects for future research is the possibility of detecting kilonovae in real time. Current observational methods rely on a combination of gravitational wave detections and electromagnetic follow-ups to identify these events. However, as technology advances, it may become possible to predict neutron star mergers before they occur, allowing astronomers to prepare their instruments and capture the entire event from start to finish. This would provide unprecedented data on the dynamics of the collision, the evolution of the kilonova, and the formation of black holes. Real-time observation of kilonovae could also help answer lingering questions about the role of neutron star mergers in galactic evolution. For instance, how do these events influence the chemical composition of their host galaxies? Do kilonovae occur more frequently in certain types of galaxies, or are they evenly distributed throughout the cosmos? Understanding these patterns could shed light on the broader processes that shape galaxies over billions of years. Another intriguing area of research involves the potential connection between kilonovae and fast radio bursts, FRBs. FRBs are short, intense bursts of radio waves that have puzzled astronomers since their discovery. While their origins remain uncertain, some theories suggest that they could be linked to neutron star mergers or the formation of magnet-ars, highly magnetized neutron stars that might arise from these collisions. If kilonovae are indeed associated with FRBs, studying these events could provide new clues about one of the most mysterious phenomena in modern astrophysics. The study of kilonovae also has implications for the search for extraterrestrial life. The heavy elements produced in neutron-star mergers are essential for the formation of planets and, by extension, the development of life as we know it. By mapping the distribution of kilonovae throughout the universe, scientists can identify regions that are rich in these elements and therefore more likely to host planets with the right conditions for life. This could refine the search for habitable exoplanets and bring us closer to answering the age-old question of whether we are alone in the universe. The more we learn about kilonovae, the more they challenge us to think about the interconnectedness of cosmic events. These collisions are not isolated phenomena. They are part of a larger tapestry of processes that shape the universe. From the birth of stars to the formation of galaxies, from the creation of elements to the emergence of life, kilonovae are woven into the story of existence itself. They remind us that even the most violent and destructive events can give rise to creation and beauty, offering a powerful metaphor for the cycle of life and death. As we continue to study kilonovae, we are not only expanding our understanding of the universe but also deepening our appreciation for the forces that have shaped it. These events, with their immense energy and profound implications, stand as a testament to the power of science to uncover the mysteries of the cosmos. They inspire us to keep exploring, to keep asking questions, and to keep seeking the answers that will bring us closer to understanding the universe and our place within it. The exploration of kilonovae also holds profound implications for our understanding of time and causality in the universe. These events occur on scales and timescales that are difficult to fathom, bridging cosmic distances and stretching our comprehension of temporal sequences. For instance, the gravitational waves emitted during a neutron-star collision travel at the speed of light, yet they can take millions or even billions of years to reach Earth. By the time we detect them, the event itself is an ancient relic of the distant past. This temporal disconnect offers a unique glimpse into the history of the universe. Observing kilonovae is akin to looking back in time, providing direct evidence of processes that occurred when the universe was younger and potentially quite different from how it is today. The light and gravitational waves from these events are messengers from the past, carrying information about the conditions of their origin. By studying them, we can piece together a timeline of cosmic evolution, from the early formation of stars and galaxies to the modern structure of the cosmos. The link between kilonovae and the age of the universe is also of great interest. By measuring the redshift of the light emitted during these events, astronomers can estimate their distance and, consequently, their age. This data can then be used to refine models of cosmic expansion and improve our estimates of the Hubble constant, a critical parameter in understanding the rate at which the universe is expanding. Discrepancies in the Hubble constant measured by different methods remain one of the most pressing mysteries in cosmology, and kilonovae could offer new insights into this puzzle. Another fascinating aspect of kilonovae is their potential role in cosmic recycling. The heavy elements ejected during these events do not remain isolated in space. They become part of the interstellar medium, the diffuse gas and dust that fills galaxies. Over time, this enriched material can coalesce to form new stars, planets, and eventually, life. In this way, kilonovae contribute to a continuous cycle of destruction and creation, shaping the chemical composition of the universe and enabling the conditions necessary for complexity and diversity. This process of cosmic recycling underscores the interconnectedness of all things. The atoms in our bodies, the elements in the Earth, and the materials that power our technology all have origins in events like kilonovae. They are the product of ancient collisions that occurred long before our solar system existed, highlighting the profound unity of the cosmos. This perspective invites a sense of wonder and humility, reminding us that we are part of a much larger story that stretches across space and time. The study of kilonovae also intersects with questions about the nature of matter and energy. Neutron stars themselves are composed of some of the densest matter in the universe, consisting primarily of neutrons packed together in a state known as neutron-degenerate matter. The extreme conditions inside these stars challenge our understanding of physics, particularly the behavior of matter at nuclear densities. When two neutron stars collide, they create conditions that are even more extreme, providing a rare opportunity to study these phenomena in detail. One of the most intriguing questions in this area is what happens to the matter during and after the collision. Does it form a black hole, as often happens in these events? If so, what are the properties of this black hole, and how does it evolve over time? Alternatively, the collision could produce a hypermassive neutron star, a temporary structure supported by rapid rotation and intense magnetic fields. These outcomes have different implications for the distribution of energy and matter, as well as for the gravitational waves and light emitted during the event. The connection between kilonovae and black holes is particularly compelling. Black holes represent the ultimate endpoint of matter collapsing under gravity, and their formation during neutron-star mergers offers a glimpse into this extreme process. By studying the signals from kilonovae, scientists can learn more about how black holes form, grow, and interact with their surroundings. This knowledge could help answer broader questions about the role of black holes in shaping galaxies and influencing cosmic evolution. Kilonovae also raise fascinating questions about the limits of detectability in astronomy. These events are incredibly bright, but they occur in distant and often faint galaxies, making them challenging to observe. Advances in telescope technology and data analysis are helping to overcome these challenges, enabling astronomers to detect kilonovae with greater precision and frequency. However, many kilonovae likely go undetected, either because they occur in regions of the sky that are not being monitored or because their light is obscured by intervening dust and gas. To address these limitations, scientists are developing new methods for identifying kilonovae. Machine learning algorithms, for example, are being used to analyze vast amounts of data from telescopes and identify patterns that might indicate the presence of a kilonova. These tools are helping to automate the search process and ensure that fewer events are missed. Additionally, collaborations between observatories around the world are improving the coverage of the sky, increasing the chances of catching these rare and fleeting phenomena. The ongoing study of kilonovae is a testament to the power of curiosity and the human drive to understand the universe. These events, with their incredible energy and profound implications, represent some of the most dramatic and awe-inspiring phenomena in the cosmos. They challenge us to think deeply about the nature of matter, the origins of elements, and the forces that shape the universe. At the same time, they offer a sense of connection and continuity, reminding us that we are part of a vast and dynamic cosmos. As technology continues to advance, our ability to study kilonovae will only improve, opening new windows into the mysteries of the universe. From the formation of heavy elements to the detection of gravitational waves, these events are reshaping our understanding of the cosmos and our place within it. They remind us that even in the darkest corners of space, there is light, and even in the most violent events, there is creation. The story of kilonovae is ultimately a story of discovery, transformation, and the enduring quest to understand the universe and our place within it. The discovery and ongoing study of kilonovae continue to reveal more mysteries about the universe, many of which redefine how we view cosmic evolution. One of the most tantalizing aspects of kilonovae is their connection to the origins of the elements that make up the periodic table. Most of the universe's hydrogen and helium were formed in the Big Bang, while elements up to iron are primarily synthesized in the cores of stars. However, elements heavier than iron, like gold, platinum, and uranium, are created in much rarer and more extreme conditions. Kilonovae are among the key sites where this process, known as the Rapid Neutron Capture Process or R process, takes place. The R process involves the rapid capture of neutrons by atomic nuclei in environments with incredibly high neutron densities. During the violent collision of two neutron stars, these neutrons are flung into space in enormous quantities, creating the perfect conditions for this process to occur. The result is the formation of heavy elements that are then scattered across the cosmos, seeding future stars, planets, and even life itself with the building blocks of matter. Without kilonovae and similar events, the universe would lack many of the elements that are essential for life as we know it. Recent studies have shown that a single kilonova can produce an astonishing amount of heavy elements, including gold and platinum, equivalent to several Earth masses. This fact alone is mind-boggling and reshapes our understanding of the universe's material wealth. The next time you see a piece of gold jewelry or handle a device containing rare metals, you can marvel at the fact that these materials were forged in one of the most violent and energetic events in the universe. They are the remnants of a cosmic firestorm that occurred millions or even billions of years ago, billions of light years away. The idea that the very atoms in our bodies could trace their origins to such an event is both humbling and awe-inspiring. It's a stark reminder of our cosmic ancestry and the intricate interconnectedness of all matter in the universe. This connection fuels much of the scientific excitement surrounding kilonovae. They are not just fascinating phenomena but also vital contributors to the cosmic cycle of matter and energy. In addition to their role in element formation, kilonovae offer invaluable insights into the behavior of extreme states of matter. Neutron stars themselves are some of the most bizarre and enigmatic objects in the cosmos, composed of matter compressed to unimaginable densities. A single teaspoon of neutron star material would weigh about 1 billion tons. When these stars collide, they create conditions that push the boundaries of our understanding of physics. The gravitational waves emitted during these collisions provide a direct way to study these extreme conditions. Unlike light, gravitational waves are ripples in spacetime itself, traveling unimpeded through the universe. This means they can carry information from the most violent and obscured regions of space, offering a unique perspective on phenomena that would otherwise be invisible. The detection of gravitational waves from kilonovae is thus a groundbreaking achievement, opening a new era in astronomy. Gravitational waves are also helping scientists test one of the most fundamental theories in physics, Einstein's general theory of relativity. This theory predicts how gravity behaves under various conditions, including those found in neutron star collisions. By comparing the observed gravitational waves to theoretical models, researchers can look for deviations that might indicate new physics beyond our current understanding. So far, the observations have confirmed general relativity with remarkable precision, but the search for anomalies continues, driven by the hope of discovering something truly revolutionary. Another fascinating aspect of kilonovae is their electromagnetic radiation. While gravitational waves provide a way to study the mechanics of the collision, light emitted during the event, ranging from gamma rays to infrared, offers complementary information about the processes occurring within and around the merging stars. This light is produced by the radioactive decay of the heavy elements created in the collision, a phenomenon that unfolds over days and weeks, providing a rich dataset for astronomers to analyze. The multi-messenger approach to studying kilonovae, combining gravitational wave and electromagnetic observations, is transforming our understanding of the universe. It allows scientists to piece together a more complete picture of these events, from their initial moments to their long-term aftermath. This holistic view is crucial for answering some of the biggest questions in astrophysics, including the nature of matter, the origins of the elements, and the structure of spacetime. The sheer scale of these investigations is staggering. Detecting a single kilonova requires coordination among observatories around the globe, as well as advanced instruments capable of capturing fleeting and faint signals. For example, the Laser Interferometer Gravitational Wave Observatory, LIGO, and its international counterparts, such as Virgo and CAGRA, play a central role in detecting gravitational waves. Meanwhile, telescopes like the Hubble Space Telescope and the James Webb Space Telescope are used to study the light emitted during these events, providing high-resolution data across multiple wavelengths. These efforts are supported by advanced computational models that simulate the conditions of neutron star collisions. These models are incredibly complex, requiring immense processing power and cutting-edge algorithms to replicate the behavior of matter and energy in such extreme environments. By comparing these simulations to real-world observations, scientists can refine their theories and make predictions about future events. Despite the progress that has been made, many mysteries remain. For instance, the exact mechanisms that govern the OR process are still not fully understood. What triggers the rapid capture of neutrons? How do the properties of the merging neutron stars influence the types and quantities of elements produced? These questions are at the forefront of current research, driving the development of new technologies and methodologies. Additionally, the role of kilonovae in galactic evolution is an area of active investigation. By studying the distribution of heavy elements in the Milky Way and other galaxies, astronomers hope to trace the influence of these events over cosmic timescales. This research has implications not only for astrophysics but also for planetary science, and the search for extraterrestrial life. After all, the availability of certain elements may determine the types of planets that can form and the potential for life to emerge on them. As we continue to unravel the mysteries of kilinovae, we are reminded of the profound beauty and complexity of the universe. These events, born of destruction, are also creators, forging the elements that make life possible and shaping the cosmos in ways we are only beginning to understand. They are a testament to the dynamic and interconnected nature of the universe, a reminder that even in its most violent moments, there is creation, transformation, and the seeds of new beginnings. The transformative power of kilinovae extends beyond the realms of science and into the philosophical questions that humanity has pondered for centuries. What does it mean for life, as we know it, to owe its existence to such catastrophic cosmic events? How does understanding these processes reshape our sense of place in the universe? These questions are not just abstract musings. They are deeply tied to the discoveries made in the study of kilinovae. When neutron stars collide, they are essentially rewriting the fabric of their surrounding space, creating conditions where the ordinary laws of physics are pushed to their extremes. This makes them natural laboratories for understanding phenomena that would be impossible to replicate on Earth. For example, neutron stars are composed almost entirely of neutrons, held together by gravity so intense that their interiors represent the densest known states of matter. When these stars merge, the resulting explosion gives scientists a fleeting glimpse into the fundamental building blocks of matter under the most extreme conditions imaginable. One particularly fascinating outcome of these collisions is the potential formation of a black hole. Not every neutron star merger results in a kilonova that disperses material into space. Some instead collapse into black holes almost immediately after the merger. The conditions under which a merger results in a kilonova versus a black hole remain a significant mystery. Scientists believe that the mass and spin of the original neutron stars play a critical role, but many details are still unknown. This uncertainty adds an element of unpredictability to the study of kilinovae, making each observation a potential game-changer. For instance, when LIGO detected gravitational waves from the first confirmed kilonova in 2017, the data suggested that the merger had left behind a rapidly spinning neutron star, a hypermassive neutron star, that eventually collapsed into a black hole. This finding challenged existing models and prompted new theories about the life cycle of such extreme objects. Another area of intrigue lies in the electromagnetic signals emitted by kilinovae. As the heavy elements created in the collision decay, they release energy in the form of light. This glow, which starts as a bright flash and gradually fades over weeks, carries a wealth of information about the composition of the ejected material. Observing these signals across different wavelengths, such as visible light, infrared, and gamma rays, allows scientists to map the abundance of elements and compare them to theoretical predictions. One unexpected discovery in this area is the role of lanthanides, a group of rare earth elements, in shaping the appearance of kilinovae. These elements, which are highly opaque to light, can cause the kilonova's brightness to decline more rapidly than previously thought. Understanding this effect has been crucial for interpreting observational data and refining models of element production. The study of kilinovae also has implications for understanding the evolution of the universe itself. Over the course of billions of years, countless neutron star mergers have seeded galaxies with heavy elements, influencing everything from the formation of planets to the chemistry of interstellar space. By examining the distribution of these elements in ancient stars and gas clouds, scientists can reconstruct the history of kilinovae and their role in shaping the cosmos. This cosmic recycling process highlights the interconnectedness of all things. The gold in your jewelry, the uranium in a nuclear reactor, and even some of the elements in your own body were likely forged in the crucible of a kilonova. This realization connects us to a lineage of cosmic events that stretches back to the dawn of time, reinforcing the idea that we are not separate from the universe but an integral part of it. Kilinovae are also helping scientists address some of the most profound questions in modern physics, such as the nature of dark matter and dark energy. These mysterious substances, which together make up about 95% of the universe's mass energy content, remain largely unexplained. By studying the behavior of matter and energy in the extreme conditions of neutron-star collisions, researchers hope to uncover clues about these elusive components of the cosmos. For example, some theories suggest that dark matter could consist of exotic particles that interact only weakly with ordinary matter. The intense conditions of a kilonova might provide a unique environment for detecting such particles, either through their direct interaction with the ejected material or through subtle effects on the gravitational waves emitted during the event. Although no definitive evidence for dark matter has yet been found in kilonova observations, the possibility remains an exciting avenue for future research. Similarly, the study of gravitational waves from kilonovae could shed light on the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. By measuring the distances and velocities of neutron-star collisions across different epochs of cosmic history, scientists can test models of dark energy and refine our understanding of the universe's expansion. This work has the potential to answer one of the most pressing questions in cosmology: what is the ultimate fate of the universe? While these scientific endeavors are undeniably fascinating, they also serve as a reminder of how much we still have to learn. Each new observation raises as many questions as it answers, revealing the vastness of our ignorance even as it expands the boundaries of our knowledge. This duality, the simultaneous discovery of answers and mysteries, is what makes the study of kilonovae so compelling. The tools and technologies used to study kilonovae are themselves marvels of human ingenuity. Gravitational wave detectors like LIGO and Virgo rely on interferometry, a technique that measures incredibly tiny distortions in spacetime caused by passing gravitational waves. These distortions are so small, on the order of a fraction of the diameter of a proton, that detecting them requires unparalleled precision and sensitivity. The fact that we can measure these signals at all is a testament to the power of human creativity and perseverance. Meanwhile, advances in telescope technology have made it possible to capture light from kilonovae with unprecedented clarity. Instruments like the James Webb Space Telescope can observe these events across a wide range of wavelengths, providing detailed data that would have been unthinkable just a few decades ago. These observations are complemented by sophisticated computational models that simulate the conditions of neutron-star collisions, allowing scientists to test hypotheses and refine their understanding of these phenomena. As the study of kilonovae continues to evolve, it is likely to yield even more groundbreaking discoveries. Future missions and observatories, such as the European Space Agency's LISA, Laser Interferometer Space Antenna, promise to extend the reach of gravitational wave astronomy, enabling the detection of even fainter and more distant events. At the same time, advancements in computational power and data analysis techniques will make it possible to extract more information from the signals we observe. The story of kilonovae is far from complete. Every new observation, every new piece of data, brings us closer to answering the big questions. How did the universe come to be the way it is? What are the fundamental laws that govern its behavior? And what is our place in this vast and ever-changing cosmos? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.